Chapter 7 is titled Exponential and Logarithmic Functions. In this chapter, we'll learn about this new type of nonlinear function, we'll solve some application problems, we'll simplify and find inverses, and then we'll work with those. In 7.1 and 7.2, we're going to look at two types of functions called exponential growth and decay. In the first part of these two lessons, we're going to sketch their graphs. An exponential function is any function of the form y equals a times b to the x power. We call this exponential. Whoa, hang on, sorry. We call this exponential because x is your exponent. Notice in this equation the a and the b are not in parentheses. So we always want to consider our property rules that we talked about in both chapters 5 and 6 and recognize that a is its own separate value from that b to the x. Order of operations, we would have to evaluate the exponent first. As we look at these types of problems, the a value will always represent the original amount of a function. And for the parent function, a will always equal 1. If we have an exponential growth, the growth factor is the b value, and b will always be greater than 1. By definition, as we look at these application problems, t will always represent the time, x will always represent time involved for these functions, and y is the new amount. So for example, the parent function will look something like this. Y equals something like maybe 2 to the x power, where a would just be 1. So y would equal 1 times 2 to the x power. You'd pick values for x, evaluate that exponent, and then multiply by 1. Now over here on the right, the graph gets infinitely close to the x-axis on the left-hand side, and once it crosses over that y-intercept, notice how big it gets. It increases exponentially. It gets really, really big, really, really fast. Another thing to note is that this function does actually not cross over the x-axis. So the x-axis is considered an asymptote. A-S-Y-M-P-T-O-T-E. Whoa, not T-O-T-O. T-O-T-E. There we go. All right. Remember, an asymptote is just a line that the function trends infinitely close to but doesn't cross over. We could even consider drawing in a dashed boundary line, kind of like we did with hyperbolas way back in chapter 9. We go all the way across at the bottom. And even though the graph would get really, really small on that left-hand side, as it goes closer to negative infinity, it would never cross over that boundary line. When we're not working with an exponential growth function, we may have something that's an exponential decay function. The template for the formula is the exact same, but now your b value is going to be a fraction between 0 and 1, and b will represent a decay factor. So an example for this kind of function might be y equals, maybe our a value is a transformation 2, so maybe a equals 2, and then we'll have 1/3 to the x power. So that would indicate a decay function. Whatever has the exponent is a fraction. Notice the graph kind of flip-flopped over the y-axis. It's bigger on the left-hand side and now smaller on the right. A way to describe this graph then is as a reflection over the y-axis. Also notice that it gets infinitely close to the x-axis on that right-hand side, and on the left-hand side it goes up forever and ever and ever. Well, that left-hand side, again, is that rule that the x-axis is going to be the asymptote. It's never going to cross over that line. So let's add that in. The x-axis is still the asymptote. As we apply transformations to these equations, however, that could change. So speaking of transformations, let's take a look at some descriptions down below. If the a value is negative, just like we worked with square root functions back in chapter 6, the graph would reflect over that x-axis. And that's one way to describe it, and way to check our graph. If you have something like a, bx, like the normal parent function, plus k at the end, so if it's being added or subtracted, the graph will move up or down by k, and whatever that value is. So if k is positive, it'll move up. If k is negative, it will move down. And also note, you have this written on your paper, but in this video it's not written there. I'm not sure why. This will also move the asymptote by that same amount. So add in the word asymptote on your graph. There we go. Also moves the asymptote up or down. Okay. At least now our notes will match. And then last but not least, the unique change comes from that exponent. If you're adding or subtracting anything to x in the parenthesis, the graph will move left or right. So very similar in concept to all the other types of functions we've ever graphed. Our square root functions, our quadratic functions, and anything that it moves left or right, it's in the opposite direction. There we go. So if you had x plus 4, it would move 4 to the left. If you had x plus or minus 2, it would move 2 to the right. All right, let's put some of this to the test with some graphing on the next page. Here we have two different equations, y equals negative 2 to the x and y equals 2 times 3 to the x plus 1. The first thing we're going to do is just kind of break down each part of our equation, and then we'll create a table. Now, noticing that negative out in front, I want to make sure we're clear on what each part represents. I'm going to rewrite y on that left-hand side, and on the right, that negative actually represents a negative 1 a value. Our base is 2, so that's going to be 2 to the x power. So if a equals negative 1, we know this graph is going to reflect over the x-axis. So we know our graph will kind of open upside down. B equals 2, so this means a growth factor. It'll be smaller on the left and bigger on that right-hand side. It'll increase faster. The other thing I want to note is our asymptote, by definition, is the x-axis, but the equation is y equals 0. So y equals 0 is the equation for the x-axis. And I'll wait to graph that until I scroll down to have a bigger view of the graph. To make a table, we're always going to start with our basic input values for x. We're going to keep this consistent. So on your table, give yourself some room to work. I want you to start with the basics from negative 2 up to positive 2. And the only time these values will change are if we change the exponent by moving it left or right. So now, order of operations. This is going to take a little while to kind of process. We're plugging in these values for our exponent and then simplifying that other side. Here's how it'll look. If I plug in negative 2, I have y equals negative 1 times 2 to the negative 2 power. Well, think order of operations. 2 to the negative 2 power would be 1 over 2 squared, which is 1 over 1/4. Okay, so think about that again. 2 to the negative 2 power is the same as 1 over 2 squared, and that's how I got 1/4. Now, negative 1 times 1/4 is just negative 1/4. Our negative a value, whoops, not negative 1/2, negative 1/4. There we go. Our negative a value is just going to make all of our outputs negative. So that's just something to be careful about as we go through this. All right, next one, negative 1. If I plug in negative 1 times 2 to the negative 1 power, that's going to be negative 1 times 1/2, which is just negative 1/2. 0 is a nice one to work with. When we apply our 0 exponent rule, remember anything to the 0 power is, think about it, 1. So if we have negative 1 times 1, that's just negative 1. All right, let's watch what happens as our x values increase. If we plug in positive 1, that would just be negative 1 times 2, which is negative 2. And if we plug in positive 2, 2 squared is 4. Negative 1 times 4 just makes our answer negative. Notice all of our outputs are negative. All right, let's see what this looks like on our graph. I'm going to start by drawing in our asymptote. Our asymptote is the x-axis, so as I kind of just draw that straight across the equation y equals 0, it's pretty much just our guide to indicate we're not crossing over that line. Now as we plot these points, we have -2, -1/4. So it's going to be kind of hard to even fit that in there. -1/4 is just below the x-axis. As we go to the right, -1 increases to -1/2, so a little bit lower. And at 0, we're at -1. So you can kind of start seeing that turn already happen. At 1, I'm going to go drop down to -2. And at 2, it drops down to -4. Sorry, I just had a sneeze right there. So you can kind of see that curve happening. On the left-hand side, we're going to get infinitely close to our asymptote line. So as you notice, if I start on that left-hand side, I'm going to be super close to that arrow and kind of just follow right along until I get to those values that we plotted. And then as the graph turns, it gets sharply, it drops down really quickly. So I'm going to have an arrow on each side. There's the sketch of a graph that reflects over the x-axis and is an example of exponential growth. Let's try the one on the right. For our next equation, y equals 2 times 3 to the x plus 1 power. Notice this already has the a and the b values separated by the parenthesis. A equals 2. That's a number that's greater than 1, so this graph is going to stretch vertically. It's going to get even bigger faster than the other exponential growth function does. So stretches vertically. And that just means, like I said, our outputs get bigger faster. The b value is 3, and that indicates another growth function. Notice a wasn't negative, so there's no reflecting this time. We have that x plus 1. So that x plus 1 is going to move everything left 1, kind of like from what the parent function would do. So that's going to change our table as well. That's 1 unit. I don't know why the I and the T didn't decide to separate there. There we go. 1 unit. There we go. All right. So that's going to change our table too. Change the x values. Just by 1, and I'll show you how to do that. Okay. And last but not least, let's write the equation for our asymptote. We didn't move anything up or down, so the asymptote is going to stay on that y or on that x-axis, but the equation is y equals 0. Over on the right, when we create our table, since the x plus 1 is going to move everything 1 unit to the left, instead of starting at -2, I'm going to start at -3. So I'm just going to write start at -3. And then we'll go -2, -1, 0, 1, and I think we'll see what happens from there. I think that's going to give us plenty of values. So still the same number of points that we had last time. We just shifted everything 1 unit to the left. All right, so plug everything in for x, and then we'll see what we get for our outputs. So right up there. When x equals -3, we have 2 times 3 to the -3 plus 1. Well, -3 plus 1 is -2. 3 to the -2 would be 1 over 3 squared, so that's 2 times 1/9. 2 times 1/9 is just the same as 2/9, so not a very big output answer. 2/9 is way less than 1. All right, -2. If we type in -2 plus 1, that's 3 to the -1 power, which would be the same as 1/3. And 2 times 1/3 is 2/3. Bigger than 2/9, but still pretty small for an output. -1. If we type in -1 plus 1 for our exponent, we get 3 to the 0 power, and 3 to the 0 power is 1. 2 times 1 is 2. Go to 0. 0 plus 1 is 1. 3 to the first power is 3, and 2 times 3 is 6. So we're starting to really increase our values. Watch what happens when we go to the next number. 2 times 3 to the 1 plus 1 power. Well, 1 plus 1 is 2. 3 squared is 9. 2 times 9, it already goes way off our graph at 18. So it didn't take very long for that to happen. Let's go ahead and plot these points to take a look at what this growth function looks like. First, I'll draw in my asymptote, just that boundary line. We always want to draw that in. Kind of hard to see it on the x-axis, so make sure to draw your arrows off to the edges so that you can tell it's there. Or if you have a different color, again, this would be a nice time to incorporate that. All right, let's plot our points for this growth function. At -3, we're way down at 2/9, which is really, really close to that x-axis. At -2, it gets a little bigger to 2/3. At -1, it goes all the way up to 2. So just like that, we really see a big curve starting to happen. 0 up to 6, and then 1 goes to 18. So already way beyond our graph. So 1 is like, I don't know, way up here somewhere. As we connect these dots, again, following that rule, it's going to get infinitely close to that x-axis, and then all of a sudden just cruise right through those values super, super fast. Whoops, I missed that one. All right, let's see if I can get a little closer to that after I go through there. So it's going to increase over here. Oh, I'm closer. All right, we'll call that our second exponential growth function. Our final graph for today's video, y equals -1/2 times x minus 3 plus 2. This equation is pulling out all the stops. We have a negative out in front. Now we have a decay function instead of a growth function. We're going to move the graph left and right, and notice at the end we're also going to move the graph up too. Let's first kind of get everything in order. That negative out in front indicates a is -1. And then our decay factor, 1/2, x minus 3, and plus 2. If a equals -1, the graph is going to reflect over the x-axis. So it'll be upside down. b is 1/2, so this is a decay function. It's also going to reflect over the y-axis. Sorry for all the tapping on my laptop here. All right, so let's see. We have x minus 3, and that means we're going to move everything to the right 3 units, including our table. So we'll talk about that in just a moment. Let's see, what else are we doing here? Oh, that plus 2 at the end. The plus 2 is going to move everything up 2. And I wrote this one last because this also changes our asymptote. So the asymptote, because of that plus 2, isn't going to be y equals 0 anymore. It's going to be y equals 2. So we'll see what that does to our graph when we're done. So let's go ahead and create our table. I've created my graph. Recognizing, remember that x minus 3 moves everything 3 units to the right. Normally we said to start at -2 for the x values. We did -2, -1, 0, 1, 2. But if we move 3 to the right, that's going to move us over all the way to 1. So I'm going to go 1, 2, 3, 4, and 5. We'll see if we can add any additional points at the end. I think we may throw in a couple more on this one, but I'm spreading these out to give us room to kind of calculate what this looks like on that right-hand side. So if I plug in 1, the reason why I kind of made all this space, we're going to have negative, and then I've got 1/2 to the 1 minus 3 power plus 2. So we've got to kind of figure all this out. Well, 1 minus 3 is -2. So that would give us -1/2, or negative times 1/2 to the -2 power plus 2. Well, if we have 1/2, there's a 1 right there. If we have 1/2, wow, never mind. Let's just kind of fix that because that really is not nice to look at. All right, sorry everybody, 1/2, there we go, to the negative 2 power. If you have a fraction with a negative exponent, that becomes negative and then 2 squared plus 2. 2 squared is 4. Negative 4 plus 2 would be negative 2. So this is a lot of messy work for an output of negative 2. Sorry about that. Hopefully you had enough space to write that out, or even put it over at the top or down here at the bottom, wherever you have space to show this work. Totally a good idea to do that. At 2, we have negative 1/2. 2 minus 3 is negative 1. I'll just kind of clean up my space a little bit there, plus 2. So 1/2 to the negative 1 will just be 2. So it just flips, takes a reciprocal. And negative 2 plus 2 would put us at 0. 3, if we have negative 1/2, 3 minus 3 is 0 plus 2. 1/2 to the 0 is 1. Therefore, negative 1 plus 2 is positive 1. All right, let's keep going. 4. If we do 1/2 to the 4 minus 1 power, that's just 1 plus 2. Negative 1/2 plus 2 is just 1.5 or 1.5. And then if we do negative 1/2, 5 minus 3 is 2, so we're going to square negative 1/2. That becomes negative 1/4 plus 2, and that would give us 1.75 or 1 3/4. So let's plot these points and see what happens. I need to zoom out my screen here, so hang on. Here we go. All right. So over here on the right, if we plot these points, we've got 1, negative 2, 2, 0. So notice now we're on the x-axis this time because our asymptote moved up. Oh, the asymptote. Totally forgot. Let's go ahead and plot that y equals 2. I blame it on daylight savings time. I'm doing this on Sunday, and I'm just not quite used to that time change. So we'll go with that. Okay, so we had 2, 0 we plotted. 3, 1. So we're kind of starting to turn a little bit here. 4, 1.5. So notice how we're getting close to that asymptote. Our rule still applies when we translate that up and down. At 5, we're at 1.75. So we're getting up there really close. Now I'm going to go back to the left. I want to type in 0 for x. And I know that just means another point to plot, but it looks like we'll be able to fit that on here. And the more points we have, the better chance we're going to have at an accurate sketch for this function. If I plug in 0 at the very top, we get negative 1/2 to the 0 minus 3 power. And 0 minus 3 is negative 3 plus 2. So 1/2 to the negative 3 power would be the same as negative 2 to the positive 3 power plus 2. 2 to the third power is 8, and negative 8 plus 2 is negative 6. So if I go to 0, negative 6, that just gives us a nice point to connect with all the others. So as I sketch this graph from left to right, I notice that it's really, really low on that y-axis, or just on the left side of that y-axis. It's going to come up through that 0, negative 6, and slowly start to make its way over to these points up here at the top, and then just takes that turn and follows it, oh boy, right along that asymptote line. And these are some examples of what exponential growth and decay functions will look like.